Okay, let's go over formula names. Basically, we're going to worry, for the most part, two types of formulas: ionic compounds and molecular compounds. You've already got a little bit of introduction on the ionic compounds. Basically, that comes down to doing the names of the cation and the names of the anion, and then just putting the two together. We'll also talk a little bit about molecular names, which is totally different, and it's based on prefixes. Okay, as I said, ionic compounds, their names are basically two names stuck together. You were given a sheet that has a whole bunch of ion names on it. One column had all the positive ions, the cations. The other one had other column had all the negative ions, the anions. And basically, you just put the two parts together and you have your name. So, for example, here I have MgOH2. If I look in the left column, the Mg, well, that's magnesium. I look on the right column, OH is hydroxide, so the name is magnesium hydroxide. Second example here, if I look on the left column, NH4, that is called ammonium. PO4 is called phosphate, so this compound is ammonium phosphate. You just put the two names together and you have the name of the compound. Now, if I have something inside parentheses, that is because it's a polyatomic ion that in order to balance charges, I needed more than one of. Just because I have more than one does not mean the name changes. In other words, here we have our magnesium hydroxide, which to balance charges, I needed two of them. On the other hand, sodium hydroxide, sodium is a +1 charge as an ion. Hydroxide is a -1 charge as an ion, so I only need one of each. Sodium hydroxide. They're both hydroxide. I do not change how I say the name just because this had one and that one had two. It's just two parts. The cation name, the anion name, and nothing else. So this one's magnesium hydroxide, and this one's sodium hydroxide. And again, if when I balance my charges so that my compound's neutral, I have a polyatomic ion that has to be more than one. Okay, magnesium, column 2, alkaline earth metals, +2 charge, 2 valence electrons. Needed two of these in my crisscross, but it doesn't change the name. So here is the list that you had of the positive ions. Only one of the positive ions is a polyatomic. All the rest are basically metals, exception of hydrogen, but all of these have positive charges. A lot of them are in the transition metals. Now, if you paid attention to the list, you will notice that some elements have more than one oxidation state. That means they could have more than one charge. For example, here on this part of the list, antimony can have a +3 charge or a +5 charge. Titanium has a +3 or a +4. Basically, we use Roman numerals to tell them apart. The Roman numeral matches the charge. So an antimony 3 has a +3 charge. An antimony 5 has a +5 charge. Zinc doesn't have any. Okay, some of them don't have what we call stock numbers, don't have the Roman numerals. So that means that one basically only occurs as a +2 charge. So not all of them do this, only some. Aluminum is another one. You're only going to find aluminum with a +3 charge. But some of them do have the Roman numerals. And the nice part about the Roman numerals is they match the charge. So when you see that Roman numeral in the name, you already know what its charge is. You don't have to do any kind of crisscross in terms of figuring out what the charge would be. So What if we started with a formula? Here is antimony 3 oxide. I kind of did the crisscross backwards. In other words, starting with the formula, the 3 went over to here, 2 went over to there. Remember that as ions, I have positive and negative ions, but these are like exponents, they're up. But when they're down, there is no positive or negative sign. These don't refer to charges, they refer to how many of that particular atom is in the compound. But I can use crisscross to create the compound, or I can use the compound and basically do crisscross backwards to see what the charge would be. So here, antimony was a +3. Over here, antimony was a +5. And so then that tells me the name, antimony 5 oxide. Please note, oxygen always ends up as a -2. There are also classical names. The classical names are some of these at the end here, which ended in OUS, and some of them ended in IC. The OUS ones have one less, well, I shouldn't say one less, they have a smaller charge as an ion than the ones that end in IC. So here you see stannous, it has a +2 charge, stannic, +4 charge. Here's titanium 4 with a +4, titanus at a +3 charge. So the X always have a little bit higher charge than the OUS endings. The problem is there's no firm rule about which ones are OUS and which ones are IC. In other words, I don't know what the numbers actually are. I just know that the OUS has 1 less or 2 less. It's less than that. And that's why, in general, we don't use the classical names. We just use the stock numbers, because the stock numbers tell you immediately what the charge is. Whereas the classical name, I can compare, but I don't know what the charge is. I would have to work my way backwards. So here again, chlorine, -1 charge. Doing the reverse crisscross, I need a +3 titanium ion, balance out 3 chlorines. Over here, I needed a +4 titanium ion to balance out the 4 chlorines. Well, the +4 is titanic chloride. The +3 was titanus chloride. Okay, here is a list of all the negative ions that was on your sheet. Most of them are polyatomic. There are some patterns to it. For example, the ones that just have single elements, Br here, Cl, F, H. Notice that they all end in IDEs. And then we have some that end in ATEs and some that end in ITEs. So again, ions made up of a single element like O2-, that would be an oxygen ion, end in "ide" for their names. And some of the polyatomics that basically just have like one of each, 1 oxygen, 1 hydrogen. They don't end in oxygen. That's called hydroxide. However, a lot of them end in ATE or ITE. So for instance, here's nitrate, nitrite, sulfate, sulfite, and even down here at the bottom, phosphate and phosphite. The thing is, the eights always have 1 more oxygen than the ites. So here is nitrate, NO3 minus. Here is nitrite, NO2 minus. Sulfate, SO4 2 minus. Sulfite, SO3 2 minus. So the eights always have 1 more oxygen. However, their charge doesn't change. So these two, nitrate, nitrite, both -1. Sulfate, sulfite, both -2. Both the phosphate and phosphite have -3 as their charge. So, how do we write the formulas if we have a name? Well, first, we write out the cation and anion with their charges. So, barium, look at my list. or remember that it's in column 2, barium with a +2 charge. Okay, nitrate. Go find the nitrate on the right column list, all the negative ions. It has a -1 charge. So that's the first thing we do. Now we're going to balance charges. We check to see if they're balanced already. Well, that one's a +2. That one's a -1. They're not balanced. Now we do crisscross. However, something we didn't do before, we use parentheses if we need to for the polyatomics. So in this case, I'm going to need 2 NO3s, so I have to use the parenthesis when I move that 2 in the crisscross. And there is the balanced, if you will, chemical formula for barium nitrate. Ammonium sulfate. Okay, all these are going to be 2-word names. We write out the cation and anion, NH4, plus the only polyatomic for the positive ion, SO4 2-. We see if they're balanced. +1, -2, not balanced. Okay, do the crisscross. And in this case, since I need 2 NH4s in the crisscross, I have to put it inside parentheses. And so there's my formula. NH4, 2 SO4. Iron 3, notice this one has the stock number, iron 3. So I know that when I write out the cation, the iron is going to be a +3 charge. Chloride, one of my halogens, -1 charge. Again, check to see if they're balanced. They're not. Crisscross. However, no parentheses because the parentheses only go with polyatomic. Okay, that's just Cl. There's no other element with it. So it's just Cl 3 times. Okay, magnesium carbonate. Again, go find the anion, magnesium, column 2, +2. Carbonate is CO3 2-. Check to see if they match. These ones match, +2 and -2. It is balanced. When it's balanced, no subscripts. Okay, that CO3, the 3 goes with the CO. Okay, so that's carbonate ion. It doesn't have a parentheses and any additional subscripts, any additional numbers. And I always write the positive one first and the negative ion second. All right, now something I didn't get to mention at all last time, molecular compounds. Okay, basically the idea behind them is we have a prefix, a name, and then another prefix and name. The second name always ends in "ide." For example, P2O3, we have diphosphorus trioxide. The prefix you see in red there, the di for 2 phosphorus, the tri, 3 oxygens, and then the oxygen ended as oxide. Second example, we have carbon tetrachloride, 4 chlorines, ends in ide. To remind, molecular compounds, covalent bonds, they just have nonmetals. The smallest piece is the molecule. They're not held together by opposite charges. We can't use charges to figure out how many of them there are. We can't do crisscross. They don't use charges. However, the prefix tells you how many you need. Or to put it another way, you put down the prefix for how many you had to have in order that all the orbitals and shells were full. Now, here are the prefixes. You might want to write these down real quick on, say, the back of the worksheet that says molecular compounds. These are the prefixes. So maybe write these real quick on the back of the sheet that has naming molecular compounds. So these are what go in front of the element name. Mono for 1, di for 2, tri for 3, tetra 4, penta, hexa, hepta, octa for 8, nona for 9, deca, like decade, for 10. And again, it's just prefix, name, second name is going to have an IDE ending. There is one exception, however, to using these prefixes. We can use mono if it's for the second element. We do not use mono for the first element. So in other words, we can have something like carbon monoxide, but we're not going to have monocarbon monoxide. N2O. Di-nitrogen monoxide. Di for 2, I have 2 nitrogens. Mono for the 1 oxygen. Please note that the first name is going to be just like it is on the periodic table. Nitrogen, sulfur, oxygen, phosphorus, whatever is the first element. The second one, however, is going to end in IDE. So it's going to be changed a little bit from what it says on the periodic table. So oxide for oxygen, fluoride, chloride, halogens, sulfide, phosphide. That's the way the second name is going to go. Okay, now I've moved the 2 over. Nitrogen dioxide. Again, no mono for the first element, and then the di goes with the oxygen this time. Okay, a little bit more here. Dichlorine heptoxide. Though sometimes I have seen it as heptaoxide as well, without the contraction of the A and the O. PBr3. Phosphorus tribromide. Tri for the fact we have 3 BRs. CO2. Carbon dioxide. So, in a sense, molecular are a lot easier to do the names with than the ionic. There's no balancing of charges. There's no crisscross. There's no stock number or classical name. The prefix tells me how many are in the compound, or if I have the formula already, then I know what the prefix has to be. And really, the only thing that I have to pay attention to is the first one, it's whatever's on the periodic table, and the second name ends in IDE. All right, what about this one? Do you think it's going to end dichloride? No, it will not end dichloride. It's not a molecular compound. It's ionic. Barium is a metal. Okay? This is here because some of you, when you're doing the worksheets, you're going to think, oh, chlorine 2 there, I should make it di. No, that's only when everything is a nonmetal. Then we use our prefixes. We do not use the prefixes for the ionic compounds. Now, a special type of molecular compound are the acids. And the thing about acids is, all I got to do is put an H in front of any of those polyatomic negative ions, and it's now an acid. They all start with H. The number of H's depends on the charge of the polyatomic ion. There'll always be some next to that anion. It's the anion that determines the name, because they all have H. All acids have H in front. It's the anion that determines the name. For example, if the anion is attached to a hydrogen, ends in "ide," think like chloride or sulfide or oxide. If that's how it ends, then we put a hydro in front and then the IDE ending gets changed to IC. So this would have been hydrogen and chloride. It becomes hydrochloric acid. Here I have a hydrogen ion and a sulfide ion. That becomes hydrosulfuric acid. Again, since all we've got besides the hydrogen is just elements, they're not polyatomic, they're not ending in ATE or ITE, I put a hydro in front, change the "ide" to "ic", and then also say acid. Okay, what about the ones that end in ATE or ITE? Well, if they end in ATE, we change that to "ic", similar to what we did before, but there's no hydro in front now. So HNO3, the NO3 is a nitrate ion. It's on your list. Again, you won't have to have the list memorized. You just go down the list until you find NO3, and then you go, oh, that's nitrate. Well, if I put an H in front, and I only need one, because NO3 has a -1 charge, that nitrate ion turns into nitric acid. Anytime they end in "ate" or "ite", I will not have the hydros in front. What if it has an ITE ending to the polyatomic ion? Well, as an acid, it gets changed to OUS. So nitrite, which is NO2, notice again how it has one less oxygen than the nitrate. That nitrite gets changed to nitrous acid. Phosphite would be changed to phosphorus acid, whereas phosphate gets changed to phosphoric acid. So the "ates" always go to "ic", the "ites" always go to "us". There are a couple on the list that have additional rules. Sometimes the acid has one more oxygen even than the "ic" type name. We have to add an extra prefix of "per". So for instance, HClO3, the H, that's hydrogen. The ClO3, that's a chlorite ion. That gets changed to "ates" go to "ics", chloric acid. But there's also a compound that is HClO4. Notice it has one more oxygen on it. So this becomes perchloric acid. We have to add that little "per" basically to tell people, oh, there's an extra oxygen on the chloric part. If there's one less oxygen than the OUS acid, we have to add the prefix hypo. So for example, HClO2, notice that this has one less oxygen than it was up here. The OUSs, the ites, always have one less than the ates. The ites turn into OUS, but there is also HClO, which has one less oxygen. And so that gets a hypo in front of the chlorous acid. Now there's only a couple of these on the whole list. Most of them are ending in the "ide", the "ate", or the "ite". So again, just quick summary of some rules for the acid formulas. The hydrogen always goes first. The name will tell you what anion to use. So sulfate, or should I say sulfuric, tells you sulfate. Phosphoric tells you phosphate. Nitrate tells you, the name will tell you. You got to make sure you have enough hydrogens to cancel out the charge of the anion. Is there a hydro in the name? If there's a hydro in the name, then you know that you need one of the ions that ended in IDE. If there's not a hydro in the name, then you know that it ended in ATE, or excuse me, it ended in IC or OUS, and all the ones that end in IC came from 8, and all the ones that ended in OUS came from ite. So if you saw phosphoric acid, hey, 8 comes from ic, so I need the phosphate ion. Here, sulfurous, well, the us comes from ite, so I need the sulfite ion. And the hydrofluoric, notice hydro, so I needed a fluoride ion, and that's just fluorine. Also note this, on your list, phosphate, -3 charge, needed 3 hydrogens. Sulfite, -2 charge, needed 2 hydrogens. Fluoride, -1 charge. All the halogens are -1 charge. Just needed 1 hydrogen.